All right, so in this video, we're going to learn L'Hopital's rule. This is L'Hopital's rule. If the following three conditions are true, if you have an indeterminate form of type 0 over 0 or infinity over infinity, like we've just looked at, and your numerator and your denominator functions are differentiable, and the derivative of the denominator is not 0 for x values near a, then what must be true? The limit as x approaches a of this function, f divided by g, is the same limit as x approaches a of this totally different function, f prime over g prime. Now, I'm trying to make this cute and memorable. Do not confuse L'Hopital's rule with quotient rule, right? So what I want you to do is pause this video, and I want you to write out what is quotient rule for and whatever you remember about quotient rule. And then what's L'Hopital's rule for? It's for a different thing. And try to, I know we have L'Hopital's rule written right here, but try to flesh out what's it for, what are the ifs and what are the then statements, okay? So I'm gonna recommend that you hit pause right now before we discuss this together. All right, so quotient rule is used to take the derivative of a quotient of two functions, right? So say you were given y is equal to f divided by g and asked to find y prime. Well, then quotient rule tells me that y prime is low d high minus high d low over low squared. Remember what y prime is. It's a function that's telling us that instantaneous rate of change of y with respect to x. That is, it's telling us the slope of the tangent line at any point on the curve y is equal to f divided by g at any point in the domain. Yeah? So that's what y prime is. That's what that derivative is. Very, very different question than the one that we use L'Hopital's rule for. L'Hopital's rule is used to evaluate the limit of two functions. So here is the question. It's not what's the derivative. The question is, as x gets close to a, what do the y values get close to on the curve y is f divided by g? And the answer is that if 1, 2, and 3 are satisfied in L'Hopital's rule, these three statements, if those are true, then we can evaluate this limit by asking ourselves a totally different question, this limit, right? What we're saying here is we're saying that x values near a on the blue curve, y is f divided by g, get close to the same y values as on this totally different curve, this different function that's f prime divided by g prime. Let's go ahead and use L'Hopital's rule. All right. So example 3, use L'Hopital's rule to evaluate this limit. And this is the limit that we did in example 1a graphically. And I'm noticing here that the x did not print. So let's go ahead and put that in there. Okay, so before we can use L'Hopital's rule, you need to verify that you have all those if statements. So I'm going to do that in a little bit of Scratch. All right, 1, we need to have an indeterminate form of 0 over 0 or infinity over infinity, and we did that in example 1a. Right, example 1a showed we have an indeterminate form type 0 over 0. The second thing we need is we need to be able to take the derivatives of your f and your g. You need to be able to take the derivative of the numerator function and the derivative of the denominator function. So this function f of x is equal to e to the 2x minus 1, and g of x is sine x. These guys are both differentiable. So great. Let's go ahead and take their derivatives. Chain rule on this one. The derivative of e to the 2x is e to the 2x times 2 e to the 2x, minus the derivative of 1 is minus a 0. Don't need to write that. And the derivative of g, the derivative of sine, is cosine. And then the third thing is we need to say that the derivative of the denominator is not 0 for x values near wherever the heck you're approaching. And in this case, we're approaching 0. Maybe I'll write that in English. The derivative of the denominator is not 0 for x values near where we're approaching, in this case, 0. And that's definitely the case. G prime of x is cosine x, and x values near 0 on the cosine function map to y values near 1. Draw our little cosine. Here's your cosine function. All right, x values near 0 do not map to y values near 0, so we're good. All right, so by 1, 2, and 3, we can use L'Hopital's rule. I'm just going to do L hyphen H for L'Hopital's rule. Okay, so what do we have? The limit as, and maybe we can shift to black now that we're doing it. The limit as x approaches 0 of my numerator function, e to the 2x minus 1 all over sine x, is equal to, and when you use L'Hopital's rule, it's good to write a little LH or an H above the equal sign. It's helpful for your reader to know what you're using. Is equal to the limit as x approaches 0 of this totally different function, and the different function is f prime over g prime. F prime is 2 e to the 2x, and g prime is cosine x. All right, now I can evaluate this limit through direct substitution because of continuity. Everywhere I see an x, I'm going to put a 0. 2 e to the 2 times 0 all over cosine 0. And this is equal to go right here. 2 times e to the 0 all over cosine of 0, which is 1. E to the 0 is 1. We have our answer here, 2 times 1 over 1. Answer 2. Which is the answer that we got. Let's go scroll back and see that that's the answer that we got in example 1a. All right, in 1a, here is our graph. X values near 0 map to y values that are near 2. All right, so in black here, I have that function. We actually were doing it in green, might as well change it. Bloop. All right. Right, that was the graph of of e to the 2x minus 1 over sine x. It had a hole when x was 0. Now here is the graph of a different function, the derivative function. The derivative function, I apologize. The derivative of the numerator, not the derivative function. Laugh at your teachers misspeak, right? The derivative of the numerator and the derivative of the denominator, this red curve is a totally different function, but notice that x values near 0 on both the red and the green curve map to y values near green. That is the claim that you make when you use L'Hopital's rule.